Okay, good morning. Um, so before we get started on the material today, um, I want to remind you all to do a couple of things. I'm going to communicate everything for this course through Piazza, and I sent um, a Piazza activation link to everybody. I think almost everybody has done it. Maybe a couple of people haven't. So make sure you do it today, because starting tomorrow, all my communications will be going through Piazza. And you can set it up so that you receive the Piazza messages on email as well. So you can go set it up however you want. So that's one thing. So activate Piazza. The second thing is um, you need to fill out this consent form for blog posts. It's on Moodle, it's ready. It's due by the 27th of August, so 3 more days. If you don't fill this, then you won't be able to do the blog post, so it'll only take a minute. Each of these things will take just about a minute. Just go ahead and do it, get it done so you won't forget it. Other things, I have put my slides from lecture 1 and 2 here, and there are some more papers here that we'll look at later, but this is the place where I throw in some extra reading material and so on. So the Moodle part is ready. If you get the Piazza done starting tomorrow, you'll get all my messages. I haven't sent any messages via Piazza yet, because I can still see that 2 or 3 people haven't gone and activated it. Okay. Also, let's see. I think most of you know this, but the video lectures are posted by Engineering Online, as well as the scanned lecture notes, and there is a link on Moodle to that site. So you should be able to get there pretty easily. If there is a problem, let me know. Okay. Any questions before we start? So in the last class, we were talking about definition of chord line and angle of attack for flapped airfoil, and I was mentioning how the chord line is usually kept the same as that of the original unflapped airfoil, even if you have a flap. And one of the reasons for that is because we frequently compare CL alpha curves for flapped, unflapped airfoils all together, and that makes sense only if you keep the same chord length and the chord line. So that's what we'll start today on lecture 3 with. So we haven't talked about lift coefficient yet, but we will very soon, probably today. But I'll go ahead and use this, it will start making sense later on. So frequently you will see curves like this. So this is CL versus alpha, and let's say you have an unflapped airfoil that's this way. And the flapped airfoil may be something like this. So this is flapped, and this is the baseline unflapped. So CL is lift coefficient. It's just a non-dimensional way of talking about the force, lift force. Now this makes sense only if you use the same chord line, both the length and the angle, right? So only if you use this chord length and this chord line for both the cases, only then you can really do this. So this is same as if you plotted lift versus angle of attack. Lift in newtons, this is angle of attack, and then you can say that something like this. This is for the same, this is for a given density and velocity and yeah. So if the air density and the velocity of the free stream are the same, then this is how the lift will change. For example, I am just throwing out a pretty random example. Let us say you have a flapped airfoil and an unflapped airfoil. This is how the lift will change per unit span. So this is really per unit span. So the force, the lift force doesn't depend on how you define the chord. Lift force is just a force. But for convenience we use everything in coefficient form, and what happens here will be exactly mirrored in the CL versus alpha curve, but only if you use the same chord line. So this works. And that's one good reason to use the same chord line. Okay, so that's just a quick mention about the chord line. So we are now going to look at the flow past an airfoil, just a generic airfoil. Okay, so let's look at the velocity flow field. So when you have an airfoil at some angle of attack, so let me draw a generic airfoil, and this is the chord line. If this is at some angle of attack, so maybe let's draw the free stream as tilted. So far upstream the free stream is like this, and so maybe your stagnation streamline will look like this, and you will have streamlines around the airfoil that look something like this. So this is in this is the velocity field in steady inviscid flow. That means we are not considering viscous effects here. It's the flow field is assumed to be steady. It's steady but also inviscid. That means we are not right now looking at boundary layers and stuff like that. So you will get some flow field like this. These are the streamlines. And at any point you will get a vector for the local velocity, which is a function of xy. So v is a vector, and this streamline is called the stagnation streamline. this one. So somehow I'll try to denote it with a thick line just for the purposes of illustration. Okay, it doesn't mean that streamline is thick or anything like that. It's just, this is the stagnation streamline. And this point is called the stagnation point. And this is the point at which velocity equals 0. So here is V infinity. So because velocity becomes 0, we call it a stagnation point. So the flow comes to a standstill there at this point, it's stagnation. And that streamline is called the stagnation streamline, the streamline that goes and hits and becomes the stagnation point. The point at the trailing edge, the flow here may or may not be a stagnation point. That will depend on the trailing edge shape, and we will see that soon. So V can either be 0 or V may not be 0 here at this location. Okay, so this is all well and good. If you run the airfoil through some kind of CFD code, this is typical of the sort of results you will get. But of course, most Navier-Stokes code will also have viscous effects in the results, so it will look a little different, but generally you'll have some flow solution like this. But from the point of view of airfoil characterization and airfoil design, what is more of interest is the surface velocity distribution. So we normally don't care a whole lot about the flow field, we are more interested in the actual velocity along the airfoil surface from leading edge to trailing edge. Any guesses as to why? Why should that be more important and the flow around it less important? It will give the pressures. Okay. That's one reason. Yes. Anything else?
You can check for turbulent flow boundary separation across the coil.
Kind of, yeah. So the velocity along the surface is what determines boundary layer behavior, and boundary layer behavior governs a lot about how the airfoil behaves. So for example, when you take an airfoil to high angle of attack, it's going to stall. Why does it stall? It's because the boundary layer is not able to stay attached, and so on. So from a practical viewpoint, surface velocity distributions are of primary interest. And this is what we'll be focusing on a lot in this course. Okay, so because we are going to spend a lot of time on surface velocity distribution, let's get some sort of notes put together on how those are done. So let's talk about some things we normally do. So usually we plot the airfoil Okay, so normally just for standardization, when you're looking at airfoils by themselves, these are the things you normally do. And chord length is usually made equal to 1. Again, this helps to make plots in a standard way, and it's just very convenient to do that. So even though the physical chord length on an airplane may be, I don't know, 1.2 meters or something like that, you non-dimensionalize it to 1 and do all the thinking and calculations for the airfoil on that. And we normally put the leading edge at x equals 0 and trailing edge at x equals 1. And because the chord length is 1, we often refer to the x and y axes as they're usually referred to as x over c and y over c axes. So that's what you mean. Sometimes you might just say x and y, but what you really mean is if the chord is 1, you're really talking about x over c and y over c. So the airfoil geometry plot typically looks like this. So this is the trailing edge, and this is at 1, this is 0, trailing edge is at x comma y equals 1 comma 0, and the leading edge is here. So there are occasional times when you deviate from this. An example will be if you have a flapped airfoil. So if you have a portion of the trailing edge is a flap that's nested in the airfoil in the usual baseline configuration, and then it comes out, right? Then you still keep this as the axis, and then you'll put the flap here. So the flap itself will come beyond x equals 1 maybe. So those are times when you don't rotate the airfoil and squish it down to from 0 to 1. So this is usually done for the baseline airfoil, and then the flap can come out because we usually keep the same chord length for the flap, right? Yeah, it's the same thing with slats. And the purpose is often you want to compare those changed configurations to the baseline unflapped, unslatted configuration. And you can do that with lift coefficients and drag coefficients only if you have the same reference lengths. Okay. So let's look at an example velocity distribution. So here is some airfoil. So the chord length is 1. And this axis is V over V infinity. So I'm just drawing a grid to help illustrate this. So normally we draw, the vertical axis is v over v infinity, because velocity is, it makes sense to non-dimensionalize the local velocity with the free stream velocity. That way this plot will be valid whether the free stream velocity is 100 miles per hour or 200 miles per hour or whatever, right? So it's just convenient to non-dimensionalize it that way. But because we always draw v over v infinity, sometimes this is just called v, just for short form. We normally mean, even though we say v, it's v over v infinity. Okay, so here is some sample velocity distribution. Okay, so this point corresponds to velocity of 0, right? So on the vertical scale this point is at 0. So the velocity origin is at 0, 0. So what is this point called? Stagnation point, and that point will correspond to some point here. So right below this, I'm drawing the geometry of the airfoil here, but you don't necessarily always do that. I'm drawing it today in this picture just so we can connect these things. So this point is the stagnation point. So the stagnation streamline will come here. So let me mark that somehow. So this is the stagnation point. This is a typical sort of distribution at a positive angle of attack, and at a positive angle of attack the stagnation point is usually slightly on the lower surface below the leading edge, and so that's what I've drawn. That doesn't necessarily have to be the case. If you put the airfoil at a negative angle of attack, then the stagnation point will move up to the slightly above the leading edge. Okay, so just for this particular exercise I'm drawing it like this. So now there are two curves. One curve is like this, another curve is like this. So this is the upper surface distribution, and this is the lower surface. So if you want to know what is the velocity at 50% chord, for example, on the upper surface, you'd just go to the upper surface curve and read it off, and that will be like maybe 1.3 or something. Okay, like that. At 25% chord on the lower surface, you go to this curve and the velocity is 0.7, something of that sort. Okay, so that's how you read this. What does 1 mean on the velocity scale? That's where velocity on the surface equals v infinity. So this is free stream speed. So if you want to know where along the airfoil the local speed along the airfoil is equal to free stream speed, that's this point and maybe this point in just the sketch. So it just so happens that at 50% of the chord on the lower surface, the local flow along the airfoil. So this velocity is really surface tangential velocity. Okay, so everywhere the velocity is tangential. From the stagnation point, it goes towards the trailing edge, And let's look at the lower surface. So velocity is 0 here, right? And then from there velocity, the flow along the surface in the tangential direction goes this way. So as you can see, it starts from 0 and increases to free stream speed here, and then it decreases slightly to something like 0.9 free stream speed here, at least as per the sketch. Okay, and then let's look at the upper surface now. Again, all of this is tangential velocity. So from here the velocity is 0 and it goes. So when I say upper surface, that may not be strictly upper surface. It's really on the upper surface side of the stagnation and lower surface side of the stagnation. So let's look at this flow. From the stagnation point, velocity being 0, the flow goes like this to the trailing edge. So here it's for a small portion, it's actually lower surface if you look at it geometrically. But what we mean by upper surface is almost all of it is upper surface, maybe small portion of it is lower surface, but what we mean is on that side of the stagnation point. Okay. So velocity, you can see from here it really quickly accelerates to faster than free stream. That's what happens here. So from stagnation it actually accelerates really quickly. Even somewhere here it is free stream speed, then very quickly it becomes faster than free stream, and then it stays faster than free stream. Maybe let's call this, if I call this 1.3 or something. Here it is 1.3 times free stream, and then it slows down and comes to something like, let's say, 0.9 free stream speed. So that's what this plot means. So anything greater than 1 is faster than free stream. And anything less than 1 is slower. So this is a very sort of typical plot you will be looking at quite a bit in this course, and I want to explain what this means. Later on we'll talk about how this plot will change when you change angle of attack or when you change the shape or things like that. But just to get ourselves oriented, this is a typical velocity distribution. Now, like you pointed out, one of the other important things is pressure distribution, and we can connect this velocity distribution to pressure distribution. Okay, so in incompressible flow, pressure and velocity are connected by what? Bernoulli's equation, right? So in incompressible flow, Bernoulli's theorem or equation so we'll connect, and we are considering only steady flow. So in unsteady flow, there is an unsteady version of Bernoulli's equation. So let's take one point at free stream, and this is at some other point in the flow. So we are considering irrotational flow. That means this really won't be valid when you go into the boundary layer or some place like that where there is viscous losses. So as long as there are no viscous losses, what will happen? What does this equation become? So at some other point in the flow where pressure is P and velocity is V. So I've written the pressure. Yes, I mean it's just, you know, half rho V squared. Okay, so some point where the pressure is P and velocity is V, but here the pressure is P infinity and the velocity is V infinity. And then let's connect it to stagnation point. So we usually denote stagnation pressure by P0. So subscript here, subscript here is really 0, not O, right? 0 means 0 flow velocity. Is there any other term here? Half rho V squared, but V is 0 there, so it's just P0, right? So just to make sure we all understand the notation. P is the local static pressure. Rho is the fluid density. Which in incompressible flow is really the atmospheric density if you're looking at flow in air. Otherwise it will be the water density, right? And this is Greek letter rho, RHO. We use this so much in aeronautics and aerodynamics that I'm just going to be rattling off like half rho V squared, and you'll very soon, rho will be so automatically connected as fluid density. V infinity is free stream velocity, and it's really a vector, but here we are talking about magnitude. V is local velocity at some point, and P infinity is free stream static pressure. Which in an airplane flow will be the atmospheric pressure at that altitude. Okay, any questions on this? Should be, I think you've probably seen it in other places. So while we are here, maybe we can make a quick mention about the pitot-static tube. So the way free stream velocity is measured in an airplane is typically with a free stream with a pitot-static tube. So pitot-static tube is one where there are two concentric tubes So this is exposed to flow. So this is usually on the side of a fuselage or under a wing or some place like that, where so if you point this into the flow, so it's pointed into the direction of flight. This orifice measures the stagnation pressure. Which is denoted by P0 as we looked at in the last page. And this orifice, so this is really an outer tube with a lot of holes on all sides, and this measures the static pressure at this location. So in 3D this will look something like this. Okay, so this is the stagnation pressure is also called pitot pressure, and these are the static. Let me see if I can find a quick image. So here is a picture of a pitot tube. I think it looks like it's coming from below a wing. Some of these are simply pitot tubes, some of these are pitostatic tubes, and I don't know which one. This is probably pitostatic, and here is another one which is probably pitostatic, and so on, right? So there are various variations and complications to this, but broadly that's what we have. So what a pitostatic tube does is you measure P0 and P, right? P0 and P, P0 and P. From that you can get the free stream dynamic pressure in flight. And if you either know the density or use some kind of sea level density, then you can get the velocity, the local velocity. Actually no, I shouldn't be talking about this, I should talk about these two. So if you put this pitostatic tube away from the aircraft influence as much as possible, then you're trying to measure free stream conditions. So you by measuring P infinity and P naught, you can get V infinity. If you know the density, or if you assume sea level density, then you can get some sort of velocity. I mean, this quickly gets into more complications, but that's the general idea. So the other thing we use is, we are interested in pressures, but pressures themselves are kind of inconvenient to use. We non-dimensionalize it and use something called a pressure coefficient. And the reason is, if you take an aircraft and if it flies at some altitude at say 100 miles per hour, and you go and measure the pressure on an airfoil somewhere, it will be some, something newtons per meter squared. If you increase the speed, that pressure will change even though angle of attack is the same. So the pressure itself will depend on so many conditions. But if you non-dimensionalize it, then you can use it in many calculations, and you're kind of connecting it to lift coefficient, drag coefficient, like that there is a pressure coefficient. So we'll see in a couple of pages some more reasons for why you should non-dimensionalize. But for now, let's define a pressure coefficient. This is C small p, C subscript p, or pressure coefficient. So C subscript p, small p, is defined as p minus p infinity over half rho v infinity squared. And so this is the same as p minus p infinity over p 0 minus p infinity. And here half rho v infinity squared is the free stream dynamic pressure. So this is the units for this is pressure, and this is referred to as dynamic pressure. Half rho v squared is dynamic pressure, but since we are looking at free stream velocity, so this is free stream dynamic pressure. So so let's see let's see what the meaning of Cp is. So it turns out when Cp is positive, then P is greater than P infinity. So local pressure is greater than the free stream pressure. Local static pressure is greater than free stream static pressure. So this is called positive pressure. So in other words, what we are saying is, in aerodynamics where there is flow, right, we are interested in the pressure due to the flow. So if you take an airfoil and keep it here in this on this table, there is going to be pressure due to the atmospheric pressure, but that's not aerodynamic pressure, right? That's just static pressure due to atmosphere, pressing on it. In aerodynamics, what we are interested in is what does the flow do on top of that? On top of the existing static pressure due to the atmosphere, what does the flow do? And so that's why we are looking at P minus P infinity. We want to remove that static part out of it and just think about what the flow does. And so if P is greater than P infinity, that's positive pressure. Even though if you look at strictly pressure itself, there is always positive pressure even when there is no movement. That's not what we are looking at. So that's why we are thinking about Cp. And when Cp is negative, P is less than P infinity, and that's called negative pressure. So we keep talking about in very general terms, we'll say when an aircraft is flying, the upper surface has low pressure and the lower surface has high pressure, and that's why it generates lift. And what we mean there by pressure is actually we mean P minus P infinity, because that's what that's what comes from the aerodynamics. So negative pressure is also called suction. And when we say suction, we really mean suction compared to free stream or atmospheric pressure. Okay. So now we can connect Cp and velocity. So you have two relations, right? We have Bernoulli's equation, which is this on top, and we have the definition of pressure coefficient here. So can you take 30 seconds and derive a relation between Cp and V over V infinity? Go ahead and do it. Just put pen and pencil and paper together. It doesn't matter if you're wrong, just I mean, it's really straightforward stuff, but don't try to think in your head, just start putting it together. And I'll start a timer, otherwise we'll. So I'll give 1 minute. Okay, we're done. Anybody have their relationship? Okay, V over V infinity is square root of 1 minus Cp, or Cp equals, yeah. So Cp and V infinity are connected very clearly. Just be aware that often in airfoil aerodynamics, V over V infinity is written in short form as simply V. I mean, we know that we are talking about V over V infinity. So this is a pretty important relationship. It's very obvious, but you should be very familiar with it. Okay, so let's talk for, let's look again, why should we use these kind of non-dimensional coefficients? So why should we use pressure coefficient, for example, and later on why should we use lift coefficient, drag coefficient? Right, first of all, they're non-dimensional. That means it doesn't matter what units you're using. If you work here in SI units and somebody else in the industry is using English units, if you both convert to CP, you don't even have to ask what units you're doing. CP is CP, doesn't know units, right? The other reason is, so for example, why are we looking at V over V infinity rather than V itself, and why are we looking at CP? So let's take an airplane, and let's say you have a wing and you're looking at some section here. If you plot the V over V infinity that's being experienced by this particular airfoil section in flight, and let's say this is flying at some 100 knots, alpha equals 2 degrees, and altitude is 5,000 feet, something like that, just some numbers. Now if you plot V over V infinity, let's say you get some plot like this, and let's say this is pretty much incompressible flow, so we can convert V over V infinity to Cp, and let's say it looks like this, right? This is on this airfoil. Now if you build a scaled model of this, so aircraft are normally tested in wind tunnels, right? It's just standard practice. How does that work? That works because you can build a scaled model, a geometrically scaled model, and put it in the wind tunnel. There's probably no chance that the wind tunnel will produce exactly the same flight speed and the altitude, density of the atmosphere at this altitude. So this affects density. But as long as you keep Reynolds number and Mach number the same, so if you take a scaled model, so if you take the same, if you take the scaled model in a wind tunnel, but you keep Reynolds number and Mach number the same, so this is a much smaller, and you take the same section, if RE and M are the same, Reynolds number and Mach number, we'll talk a lot more about this, then you get the same velocity and CP distribution. So think about it, the actual pressures here are completely different from the actual pressures here. But when you non-dimensionalize it, the coefficients are the same. So same way, if you go to the top surface of this and go to 50% chord and you measure the velocity there and convert it to V over V infinity, and you do the same thing for this V infinity and this V infinity are completely different. But the V over V infinity here will be the same as the V over V infinity here. That's the sort of reason. This is kind of hard to explain, and you get it over some time after you use these things, but that's the reason coefficients are so useful. Okay, now let's work on an exercise to convert a velocity distribution to a CP distribution, just to get you all comfortable with it. So this is a problem for you to do in class. So I'm going to draw a velocity distribution. You convert it to CP distribution. It's just a sketch, so I'm not trying to look for equations or something like that. So this axis is V over V infinity, this axis is x over c, and we are going to say that the velocity distribution on the upper surface is like this. So here is the airfoil. This is not any kind of real velocity distribution, it's just something I am cooking up for the sake of discussion. Something like this. So convert this to a CP distribution, and basically what I'm asking you to do is these are just some general curves. So find the CP values for all these corner points and then draw them with some smooth curves. In an actual conversion practice, you'll actually have to take all these points and convert each one to CP to get the curve, but for today we are just sketching it. Okay, so go ahead and do this. I'll give you 2 minutes and plot it in your notebook. You should make it a habit to bring calculator or some, or use your phone or something. Okay. Um, do you have some of those numbers?
Number 15, is that 0 to infinity like this?
Okay. So let's make a table, velocity and CP. So basically we are going to convert all these key points to CP so that we can make the plot. The easiest one is velocity of 0. What is CP? So if you don't remember, Cp is 1 minus V over V infinity whole squared, or 1 this squared. Right? So Cp is 1. When velocity is 0, Cp is 1. And then we have velocity of 1. Let's convert that to Cp. 0. Shout out the answer, otherwise it gets boring if I keep talking. 1.2? Negative 1.4? 0.44. Yeah. Just watch out for calculation errors. Velocity of 0.9. When I say V, it's V over V infinity. And velocity of 2, negative 15. Some other answer? Somebody said negative 15. What is? It's negative 3. Okay, so if you make this plot, it will look something like this. It didn't come out too nicely. I didn't draw this line straight. It should be here. Okay, so this point corresponds to +1. So that's this. Let's go to the upper surface. Velocity is 2. So Cp is -3. So that's this. And it goes till 0.4 chord. So it's somewhere here. So the upper surface velocity distribution becomes from here to here. And then 0.9 velocity is plus 0.19. So that's here. So it's a curve something like this. And then the lower surface goes from 0 to, at 0.5 it becomes 1.2, which is minus 0.44. So that's here. So it's a curve that goes like this, and then something like this. So this is how a Cp distribution looks, and sometimes people plot it like this. One of the things you will notice is in steady flow Cp will never be more than 0.1. It will never become like 1.2 or 1.3 or 2 or anything like that. Cp is the maximum value of Cp in steady flow is 0.1, and that's at stagnation point. Because velocity of the flow can never be less than 0, right? You can't have flow magnitude, velocity magnitude less than 0. 0 is the smallest possible flow velocity. So the highest possible Cp is +1. So everything is less than +1, and some people plot like this, but the more conventional way of plotting Cp is to flip this upside down. And then when you do that, it starts to look like this. And that way you don't have to switch your thinking every time you look at a velocity plot and Cp plot. As you will see later, we'll do a lot of looking at velocity gradients. We'll say, oh, this is adverse gradient, and this pressure also, you want to think about it the same way. Adverse gradient means a slope like this. So because of that, we usually plot the Cp distribution flipped, and so it will look like this. So we usually plot the bottom at 0.1. It's called the 0, -1, -2, -3, and so on. And our particular airfoil, the upper surface is at -3 until about x over c of 0.4, and then from there it comes down to plus 0.19, right? Yeah, plus 0.19 is here, so it's a curve like this. And then the lower surface goes to minus 0.44 here, and so that's a curve that looks like this and then comes here. So we plot it intentionally upside down so that it will resemble the velocity plot. And this is how we are going to do this in the course. So if you plot the Cp distribution like this, I'll take away points, because in the course we are going to all be in a standardized way plotting it, and this is how most people plot it. There are occasionally somebody will plot it upside down, especially if they are practicing airfoil aerodynamicists, they plot it this way. So I want you to plot it that way, and in case you haven't done something like that before, in MATLAB, to flip the y-axis, How do you do it?
Reverse.
Yeah, what is reverse? Do you remember the command? The syntax? YDIR, yeah. So, nowadays MATLAB has got ways by which you can go and click on the axis and go pull down some menu and then fumble around and click something that will say plot it upside down. But you really should learn in a longer term sense. I mean, you'll get done with that plot at one particular time, but you should practice and learn to do it using command line. So once you make the plot, if you say set GCA, there are many ways to do this. This is one way. GCA is really get current axis, the axis that's on the figure that is currently active, that's GCA. And then if you say YDIR, Y direction, and you can set that to reverse. So every language probably has its own syntax, but in MATLAB, if you're going, most people use MATLAB, so this is one way to do it. So I want you to plot it like this. CP distributions are always plotted this way. So now let's talk about what this means. So what is CP of 0? Is it suction? Is it positive pressure? It's neither. That means what is that in terms of velocity? It's the same as free stream pressure, right? So velocity is also same as free stream velocity. So this is free stream pressure. And V is also equal to V infinity. That's why V over V infinity is 1. So Cp of 0 means V over V infinity of 1. Is that the stagnation point? No, that's not stagnation point. Stagnation point is this. So this is the stagnation point. Cp equals plus 1, V over V infinity equals 0. So this means what is the pressure at this point? P naught. So it's a stagnation pressure. It's pretty much the highest pressure you can have anywhere in the flow. And the way you get the highest pressure is by, like, let's say you're going in a car and you stick your hand out and do all that thing that we normally do, hey, we get lift and all that. But if you put your hand like this, that's pretty much stagnation pressure because you're bringing the flow to a halt. That's about the best, highest pressure you can get in a given aerodynamic situation. And so what is negative Cp? Is that positive pressure or suction? Suction. So suction, that means P is less than P infinity. And what does it mean for velocity? Yeah, so V is greater than V infinity. And that's like Bernoulli's theorem, right? When flow is faster, pressure is lower. So V becomes greater than V infinity, P becomes less than P infinity. And below this is positive pressure. Which means P is greater than P infinity and V is less than V infinity. And the lowest this can go to is Cp of plus 1, which corresponds to velocity of 0. Okay, so later on you should really kind of internalize this as much as possible. So later on you can compare this versus this. This is not the same velocity distribution, but I'm talking about these kind of things. This velocity of 1 means Cp of 0, velocity of 0 means Cp of 1, and so on, right? So this is, so if you look at this velocity distribution and this Cp distribution, I mean roughly wherever this is flat, where there is a slope like this also has a slope like this, and so on. And that's possible only because you're flipping the Cp axis. Okay, so reading this plot is just like reading the velocity plot. You imagine that there is an airfoil here going from 0 to 1 on the x-axis. And then, so this is the upper surface plot and this is the lower surface plot. So if you want the Cp here, you go to the lower surface plot and you say, oh, Cp there is 0. It just so happens in the sketch that means velocity, tangential velocity on the surface is the same as free stream velocity speed. Whereas here pressure is Cp is minus 3, so that means this whole area is under suction, less than free stream static pressure. Okay, so what is this? So we have Cp. What is the direction of Cp or pressure on the surface? So let's take that airfoil that we just drew in the previous page. We said from here to here it's suction, right? Which way is it pulling?
towards the airplane side.
So, yeah, okay. Positive pressure means it's pushing on the surface. Negative means it's sucking on the surface. But the surface direction changes everywhere, right? Like what will it be here? It'll all everywhere it'll be normal to the surface. That's what it means. Even though, that's my reminder to wrap up the class. Otherwise I'll keep you all here for 10 minutes longer. Okay. So if we have a Cp here, that means the pressure due to that will act normal to the surface. If we have the Cp here, that pressure is normal to the surface. So everywhere, even though pressure is a scalar, pressure does not have direction, but the force resulting from the pressure acts normal to the local surface direction, right? So here if we say Cp is positive, this is the pressure for positive Cp. Positive Cp means it's pushing on the surface, negative Cp means it's sucking on the surface. So if we draw the arrow for positive pressure, negative is opposite, right? So negative pressure will pull on the surface. So like that, pressure for positive Cp. So if you want the force, you have to take a little area and you have to say, okay, I'm going to take a little area and then I'm going to look at the Cp here, and if it is positive, then you integrate over this area and then you get the force. So pressure acts pressure results in a force that acts normal to the surface. So we'll have dF vector is scalar pressure times dA area. Actually it will be a minus, and dA is the elemental or really small infinitesimal area vector with direction pointing along outward normal. So if you have a little dA here, this is the outward normal. So that's why you put a minus here, because positive pressure will push on the surface. So and dA is defined with the outward normal. Okay, I'm going to stop here and we'll resume on Tuesday.